All right, everyone, I'm going to be talking about Lab 8, which is on the specific heat of solids. So this is a very like thermodynamic lab. So the lab starts off by introducing the equation relating Q, C, and delta T. So Q is the amount of thermal energy, C is the heat capacity, and delta T is the change in temperature. So essentially what this equation says is that C is Q over delta T. And what this means is that if that if the if the energy of some object increases by a certain amount and that results in an increase by some certain amount in the change in temperature, then taking the ratio of those two things gives you the heat capacity. And so essentially the heat capacity just tells you like how hard it is to raise the temperature of an object. So in other words, like if I increase the temperature by 1 Kelvin, then the heat capacity is like the amount of energy that Q would increase by. All right. And so there's also something called the specific heat, which is just C over M, which is uh, so essentially it's just the heat capacity per unit mass. So uh, this is just a better way of thinking about heat capacity, I'd say. Not a better way. It's a better way, like experimentally, because if you have something that's like huge, like a really ginormous boulder, it's gonna have a massive heat capacity because there's so much mass, meaning that raising the temperature of the entire boulder by 1 Kelvin would be a lot of energy. But if we look at the specific heat, then it doesn't matter how big the boulder is. The specific heat's still the same because it's the heat capacity per unit mass. And so the specific heat would be something called an intensive quantity. And then heat capacity itself is something called an extensive quantity, meaning that like if you combine two systems, it should increase. All right. And so there's another type of like energy change that's important, and that's the energy change due to latent heat. And so essentially, the example that you're going to be thinking about in the lab relating to this concept is liquid nitrogen. And so liquid nitrogen, super cold, right, as a liquid, but because nitrogen in like general room temperature, room like normal atmospheric pressure wants to be a gas, it's going to start boiling off. And so if the liquid nitrogen is like boiling off from our cup, that's going to require energy. It's going to require energy to go from this liquid to this gas here. Okay? And that energy is called the latent heat, essentially. It's like the heat of transformation. So if you have something that's a liquid and it turns into a gas, that requires some amount of latent heat. And so this latent heat is like not an actual change in temperature. So uh, like liquid nitrogen, it boils at around like 77 Kelvin, I believe. And so if liquid nitrogen boils at 77 Kelvin, to go from the liquid state to the gas state, there is no change in temperature, but there is a lot of energy required to do that. And then once it's in the gas state, then it can keep heating up, and that is a change in energy due to a change in temperature. All right, and so later on, you're going to be using this equation here to calculate the uh, specific heat of some metals, I believe. And so essentially, the main thing with this lab is that um, we're going to have some styrofoam cups, and you're going to have a scale, and then we're going to pour liquid nitrogen into the cups, and then once the liquid nitrogen's in the cups, we're going to take like metals or blocks, and we're going to put them in the liquid nitrogen, and we're going to see on the scale the change in weight of the styrofoam cup, which is due to a change in weight of the liquid nitrogen inside, because the liquid nitrogen is boiling off. So as the liquid nitrogen boils off, the scale weight is going to go down, and we're going to measure that. All right, so the first part of the lab is you're going to take aluminum, which we know the specific heat of, and you're going to do what I just said before, where we look at the change in weight on the scale. And then once we do that, you're going to use some equations they give you, but you're ultimately going to calculate the latent heat of liquid nitrogen. All right, and so they they tell you that the latent heat is expected to be 200,000 joules per kilogram, so hopefully we get something around there. And then the second part of the lab is you can do something similar, except you're going to be trying to find the specific heat of an iron sample and a rock sample. And so you're going to do that by measuring the change in mass over time on the scale. And then ultimately you'll end up getting something that looks kind of like this. And then you're going to be calculating the latent heat from the graph that you create. All right, and so they give you the equation to calculate the latent heat. But so you're going to be using the graph, and you're going to calculate that, and then you're gonna, so you can do it for the iron first, let's say, and then you're going to repeat it for the rock, which I guess they tell you is quartz. And then lastly, the thought experiment talks about a composite material. So like, let's say I have a material, and then I have like, maybe molecules that look like squares. Like, let's just say it's like iron molecules, but then also I have like, this looks like a chocolate chip cookie, but also, I don't know, let's say I just had like quartz also in this material, this composite somehow I put iron and quartz together. So if that were the case, then I would have a composite. And the question is really just asking, like, how does the specific heat of this composite compare to the specific heat of like the iron individually versus like the quartz individually? So that's really all this lab is. It's a very fun lab because you get to use liquid nitrogen, and that's cool, but obviously kind of dangerous. Like, you don't want to spill it on yourself, but I'm going to be talking a lot about safety at the beginning of the lab this week, and I look forward to doing the lab. Thank you.